Hi there. In this interview, we are going to simulate a real DevOps conversation around zero trust and network segmentation. This is not just about definitions. It is about how you think when designing secure systems under pressure. I want you to pause the video after each question and answer out loud as if you were in a real interview. Then compare your thinking with the sample response. This is designed for DevOps, cloud, SRE, and platform engineers at different levels. If you find this useful, subscribe so you do not miss the next simulated interview. Let us begin. Warm-up. Behavioral questions. Tell me about a time you had to push back on a feature or shortcut because of security concerns. A strong candidate might say, there was a situation where a product team wanted to expose an internal admin endpoint temporarily to speed up a partner integration. The argument was that it would only be for a few days. I was uncomfortable because that endpoint bypassed normal authentication flows and sat in a flat network segment. Instead of saying no outright, I scheduled a quick discussion and walked them through the blast radius. I explained how temporary exceptions tend to become permanent and how a single exposed endpoint could later be discovered by automated scans. I proposed an alternative using a short-lived VPN access and scoped IAM permissions so they could move forward without exposing the service publicly. It delayed them by a day, but we avoided introducing a risky shortcut. That experience reinforced that security pushback is more effective when you offer a practical alternative. How do you balance developer velocity with strict network controls? A strong candidate might respond, I try to avoid framing it as speed versus security. If controls are too restrictive and slow down iteration, people will work around them. So I focus on building paved roads. For example, instead of manually reviewing every security group change, I worked on infrastructure as code modules that embed segmentation best practices. Developers could provision services quickly, but those services were automatically placed in the correct subnet with predefined inbound and outbound rules. Velocity improves when guardrails are automated. The key is to make the secure path the easiest path. Describe a time when an incident revealed a weakness in your network design. A strong candidate might say, we had an internal service compromised due to leaked credentials. The attacker was able to laterally move because several internal services shared the same network segment and overly permissive security group rules. During the post-incident review, we realized we trusted internal traffic too much. We redesigned the architecture to isolate services by function. We tightened east-west traffic rules and required explicit allow rules between services. It was uncomfortable to admit the network was too open, but the incident gave us concrete evidence to justify investing in proper segmentation. Since then, lateral movement risk has been significantly reduced. Core technical and scenario questions. Let us move into technical depth. Explain zero trust in practical terms, not a marketing definition. How would you describe it in an architecture review? A strong candidate might answer, for me, zero trust means we stop assuming that being inside the network equals being trusted. Every request must prove who it is, what it is allowed to do, and whether it meets policy requirements. In practical terms, that means identity-based access control instead of IP-based trust. It means mutual TLS between services so both sides authenticate each other. It means short-lived credentials instead of static keys. And it means fine-grained authorization checks at the application layer, not just relying on firewall rules. I also think zero trust is about minimizing implicit trust boundaries. If a pod in Kubernetes is compromised, it should not automatically have network access to every other pod. We enforce that through network policies and service-level authentication. It is less about a single tool and more about a mindset shift. Now a scenario. You join a company where all services run in a single flat VPC. Any service can talk to any other service. There are some security groups, but they are broad. How would you approach improving network segmentation without breaking production? A strong candidate might respond, I would not start by immediately locking everything down. In a live production system, sudden restrictions can cause outages. First, I would observe. I would enable VPC flow logs or similar telemetry to understand real traffic patterns. Which services are actually talking to each other? Which ports are used? Then I would group services logically, for example, front-end services, back-end APIs, databases, and internal tooling. Based on observed traffic, I would define intended communication paths. Next, I would introduce tighter security groups or network policies in stages. Maybe start with database isolation, ensuring only specific back-end services can connect. Roll that out in one environment first, monitor for errors, then promote gradually. I would also coordinate closely with application teams. Sometimes there are hidden dependencies that are not documented. Communication is as important as firewall rules. The goal is to move from implicit allow to explicit allow, but in controlled increments. Another question: how does network segmentation differ between traditional VMs and Kubernetes-based environments? A strong candidate might think out loud like this. In traditional VM environments, segmentation often happens at the subnet and security group level. You isolate tiers by placing them in different subnets and controlling ingress and egress rules. In Kubernetes, things get more dynamic. Pods are ephemeral. IP addresses change, so segmentation cannot rely solely on static IP rules. Instead, you use Kubernetes network policies to define which pods can talk to which other pods based on labels. You can also layer service mesh policies on top to enforce identity-based access and encryption. The challenge in Kubernetes is that the default networking model often allows all pod-to-pod traffic. If you do not explicitly define policies, you effectively have a flat network inside the cluster. So segmentation in Kubernetes requires intentional configuration. Otherwise, the cluster behaves like a large shared broadcast domain from a trust perspective. Now consider this. What are the trade-offs of aggressive network segmentation? A strong candidate might say aggressive segmentation improves security by reducing blast radius, but it increases operational complexity. You can introduce configuration drift. You can create hard-to-debug connectivity issues. You can slow down teams if every new service requires multiple rule updates. There is also a risk of over-segmenting without visibility. If you do not understand traffic patterns, you might block legitimate calls and cause subtle failures. So I see segmentation as a risk management exercise. You start with high-value assets like databases and secret stores. You isolate them strongly. Then you apply finer segmentation where the risk justifies the operational cost. Security is never free. The question is whether the reduced blast radius is worth the added complexity. In most production systems handling sensitive data, the answer is yes, but it must be done thoughtfully. Let us go deeper. Assume you are designing a new microservices platform from scratch in AWS. Leadership wants a zero-trust approach from day one. What concrete architectural decisions would you make? A strong candidate might respond, if I am starting fresh, I would design identity as the primary security boundary. That means every workload has its own IAM role or identity, not shared credentials. In Kubernetes, that could mean using IAM roles for service accounts or workload identity features. At the network layer, I would avoid a flat VPC. I would separate public-facing services, internal services, and data stores into different subnets and security groups. Public services would sit behind load balancers with strict inbound rules. Internal services would not have direct internet exposure. Within the cluster, I would enable network policies by default and deny all traffic unless explicitly allowed. That forces teams to declare dependencies intentionally. I would also enforce encryption everywhere. TLS at the edge is obvious, but I would also require mutual TLS between internal services, either through a service mesh or native capabilities. That way, even if someone gains network access, they still cannot impersonate a trusted service. Finally, I would use short-lived credentials and centralized secret management. Zero trust breaks down quickly if static keys are scattered across environments. The main theme is reducing implicit trust and making identity and policy explicit at every layer. Here is another scenario. A developer complains that after enabling strict network policies in Kubernetes, deployments are failing randomly. Sometimes pods cannot reach the database. How would you troubleshoot this without simply rolling back the policies? A strong candidate might think through it like this. First, I would resist the temptation to disable the policies entirely. That defeats the purpose and hides the real issue. I would start by verifying whether the failures correlate with specific namespaces, pods, or rollout times. It might be that new pods are missing labels required by the network policy selectors. Then I would inspect the actual policy definitions. Are they allowing traffic based on labels that are not consistently applied? Is there a mismatch between namespace selectors and pod selectors? I would also test connectivity from inside a failing pod using basic tools. Can it resolve the database service? Can it establish a TCP connection? If DNS works but the connection fails, that points to network policy. If DNS fails, maybe the DNS service was not included in the allowed rules. In many cases, these issues come down to overly narrow selectors or forgetting to allow traffic to core services like kubedns. The fix is often not to relax everything, but to carefully expand the allowed rules to match the real dependency graph. The key is systematic debugging rather than policy removal. Let us explore trade-offs. Is network segmentation enough to implement zero trust? A strong candidate might answer, no, segmentation is only one layer. Segmentation reduces lateral movement, but it does not verify identity at the application layer. If an attacker compromises a service that is legitimately allowed to talk to the database, segmentation alone does not prevent misuse of that access. Zero trust also requires strong authentication, authorization, continuous validation, and observability. You need to know not only that traffic is allowed, but that it is expected and compliant with policy. For example, a backend service might be allowed to access a database, but it should not suddenly start scanning thousands of records per second. That is where monitoring and anomaly detection come in. So I see segmentation as blast radius control, not a complete zero trust implementation. Now consider this. You discover that multiple internal services are using a shared security group because it was convenient during initial development. Refactoring this will require coordination across teams. How do you approach this change in a mature production environment? A strong candidate might say, I would first quantify the risk. Shared security groups often mean broad access rules. I would review what inbound and outbound rules exist and what that implies for lateral movement. Then I would gather traffic data to see actual communication patterns. That helps avoid breaking legitimate flows. Next, I would propose a phased refactor. Instead of splitting everything at once, I might isolate one service at a time, creating a new dedicated security group with only the required rules. Deploy, monitor, validate, then proceed to the next. I would also communicate clearly with stakeholders. This is not just a technical change. It impacts deployments, troubleshooting, and sometimes onboarding processes. In mature environments, the biggest risk is not technical failure, but coordination failure. So I would treat it as a cross-team initiative with clear milestones. One more scenario. In a zero-trust model, how do you handle third-party integrations that require IP allow listing? A strong candidate might reason through it like this. This is a common real-world constraint. Some vendors still rely on static IP allow lists. If possible, I would isolate those integrations behind controlled egress points, such as a NAT gateway or dedicated egress proxy with a fixed IP. That way, we do not have to expose the entire network to static IP dependencies. I would also combine IP allow listing with stronger authentication. Just because traffic comes from an approved IP does not mean it should be fully trusted. API keys, OAuth tokens, or mutual TLS should still be required. The trade-off is operational overhead. Managing static egress IPs and vendor coordination can slow things down, but isolating that complexity to a specific egress layer prevents it from contaminating the rest of the architecture. Zero trust does not mean ignoring legacy constraints. It means containing them thoughtfully. Overall, the pattern you should see in these answers is intentional design. Not blind restriction, not blind trust. Every access path should exist for a reason, be explicitly defined, and be observable. Pressure and judgment questions. Let us shift into more ambiguous territory. You join a company that claims it follows zero trust principles. However, during your first week, you discover that engineers regularly bypass network restrictions in emergencies by temporarily opening wide security group rules and sometimes forgetting to close them. Leadership is aware, but says speed matters more than perfection. What do you do? A strong candidate might respond like this. First, I would avoid framing this as engineers being careless. In most cases, this behavior is a symptom of friction in the system. If people feel forced to bypass controls to ship or to fix incidents, the controls are probably too rigid or poorly automated. I would start by gathering data. How often does this happen? In what contexts? During incidents, deployments, migrations? Then I would propose guardrails instead of pure restrictions. For example, temporary elevated access with automatic expiration. If someone opens a broader rule, it could require justification and automatically revert after a defined time window. I would also push for better observability around rule changes. If we treat network policy updates like code changes with reviews and audit trails, it becomes less likely that emergency changes linger. The balance here is realism. Zero trust that blocks the business is not sustainable. But unmanaged exceptions are worse. My goal would be to design systems that allow controlled flexibility without eroding long-term security posture. Here is another scenario. A major production outage is traced back to overly strict network segmentation that blocked internal service communication during a failover event. Some executives now want to loosen segmentation globally to prevent this from happening again. How do you respond? A mature candidate might say, I would first acknowledge the impact. An outage caused by our own controls is painful and damages trust in the architecture. However, loosening segmentation globally is a broad reaction to a specific failure. I would focus on root cause. Was the segmentation policy unaware of the failover path? Were there missing rules for secondary dependencies? Was the failover scenario never tested under strict policies? Often the issue is not segmentation itself, but incomplete modeling of system behavior under stress. I would propose adding failover scenarios to chaos testing or game days while keeping segmentation in place. We should simulate region loss, dependency shifts, and verify that policies support those transitions. Security and resilience should reinforce each other, not compete. If segmentation blocks legitimate failover, the answer is refining policy, not abandoning principle. Now consider this. Your company is preparing for a compliance audit. Auditors require evidence of network segmentation and least privilege enforcement. However, you know that some legacy systems cannot meet strict standards without major refactoring. The deadline is 2 months away. What is your approach? A strong candidate might reason, I would start by being transparent internally. Hiding gaps until the audit will only create panic later. Next, I would categorize systems by risk. Which legacy systems handle sensitive data? Which are lower impact? That allows us to prioritize segmentation efforts where they matter most. For systems that cannot be fully refactored in time, I would implement compensating controls. That might include additional monitoring, tighter IAM permissions, stricter ingress and egress filtering at higher layers, or documented exceptions with clear remediation timelines. Compliance is about risk management, not perfection. My responsibility is to reduce the highest risks first and clearly communicate residual risk to leadership. The key is honest assessment and a credible roadmap, not rushed cosmetic fixes. Let us raise the stakes. Imagine you are on call. A security alert indicates suspicious lateral movement attempts inside your VPC. You suspect a compromised instance. However, isolating it immediately could disrupt critical customer traffic. What do you do? A mature response might sound like this. I would first validate the signal. Is this a confirmed compromise or an anomaly? I would check logs, flow records, and recent changes. If the risk appears credible, containment becomes priority. But I would try to isolate surgically rather than bluntly. For example, removing outbound permissions or detaching the instance from certain security groups while preserving inbound traffic temporarily. If the instance handles critical traffic, I would consider failing over to a clean replica before isolating the suspect node completely. Communication is crucial here. I would involve security and application owners immediately. Decisions under uncertainty should not be made in isolation. In zero trust, containment speed matters, but reckless isolation without understanding blast radius can create secondary incidents. The goal is controlled containment with minimal collateral damage. We have covered a wide range of scenarios around zero trust and network segmentation. If you followed along seriously, you probably felt some tension in these questions. That is intentional. Real interviews and real production environments are rarely about perfect textbook answers. They are about trade-offs, uncertainty, and judgment. Ask yourself, which question made you uncomfortable? Was it balancing speed and strict controls? Handling executive pressure after an outage, or managing a suspected compromise under live traffic? Pause the video and reflect on your own answers. Would you default to tightening everything, loosening everything, or stepping back to understand context first? Strong engineers do not chase absolutes. They think in terms of risk, blast radius, operational reality, and long-term maintainability. If you found this useful, subscribe so you do not miss the next simulated interview. Each session is designed to challenge your thinking, not just your technical vocabulary. And before you leave, tell me in the comments which scenario was hardest for you and why. That reflection process is often more valuable than the sample answers themselves. I will see you in the next one.